let's do this more. All right. So let's say that we go to your bank, right? And you type in your password, right? And maybe your password has in bits to it, right? And so now we're going to get in a little bit how the standard RSA encryption works. All right, that's what banks are using now, RSA encryption. Maybe you've heard those letters, right? What do they do? I don't know how it's, if my password is, the name of my dog, I don't know how they translate that into primes, but more or less, my password are two randomly chosen in-digit prime numbers. All right. So how do I get that? Well, if I write down some prime, I can say, give me the next prime. And now that's something that we can do, right? I can say, give me the next prime. And here's, in fact, a general rule of knowing is an algorithm polytime or exponential time. If a program like Wolfram and Alfram is willing to do it, then it's polytime, right? And if they're not willing to do it, it's because it's exponential time. All right, I got my two prime numbers, right? Then what do? I multiply my prime numbers together to get a capital N, the big number, right? How long did it take me to do that? N squared time, right? I can do that certainly if I have a computer, right? Everybody good? So the time is N squared. Right? We got 14 characters. Took me 196 operations. Not so bad, right? Everybody good? All right. Now, I make this product known to the entire universe. I publish it in my phone book, more or less, right? So everybody knows that the P and the Q are my password. Nobody knows my P and Q except for me, right? But everybody knows the product of my P and Q. All right? All right. So the factoring, right? The P and the Q is my password, right? Everybody get that? All right. So now here's the burglar. He knows the product. All he has to do is factor them. Right? I give you 12. That's 2 times 2 times 3, right? Easy. Factoring's easy, right? Right. So what's the best? Right? All I do is I have to factor them, and then I can steal your money. Right? Everybody buy this? Seem like a dumb scheme? All right. Well, let's come up with an algorithm for factoring. I check, does 2 divide into it? Does 3 divide into it? Does 4 divide into it? Right? Each time I check, does it divide? That's an algorithm, right? Now, there are algorithms that are a little faster, like you only have to go up to the square root of n, for example, and then you can do fancy sieves and things and do a little faster, but more or less, this is what we got. All right? Yeah? Yeah, let's stay on topic. All right? All right, so now let's calculate the running time of this algorithm. Right? Well, it's looping. It's dividing in time. I'll let you divide in constant time because I'm nice. It's order n. Right? But how does big N relate to little n? Big N is a value, right? Right? It's linear in the value. It's not linear in the number of digits, right? How many digits do I have? Well, before there were 14, so when I multiply, it goes double the number of digits. So now I have 28 digits, right? The value is 10 to the 28, right? So what's so this is called a one-way function. I can multiply two numbers. If I have two n-bit numbers, I can multiply them in n squared time. Polynomial, no problem, right? But to factor them out again takes exponential time, right? It's just the nature of the beast, right? Right? I give you this capital N with 28 digits. It takes me 28 digits to give it to you, but time to give it to you. And then you have to more or less count up to the value, right? Everybody get it? All right, so that's bad. All right. All right, everybody get that? And it's why our banking system works. Now, it turns out that if they come up with the it turns out that there's a quantum algorithm that factors fast. So if you can build a big quantum machine, it will break everybody's passwords, right? Everything that, you know, Trump is declassifying John F. Kennedy dying, right? But everything will get declassified, right? Now, do we have to worry about not having encryption? No, there are other encryption systems that are more complicated, but we're not currently using them. All right, now people feel like they probably sort of understood that, right? But I sometimes put this on a test and people get it wrong, all right? And so here's a very simple algorithm. I give you a value capital N, and you say high that many times, that value times, right? And then what's the running time of this algorithm? How many people say it's linear time? How many people have a different answer? Anybody want to say exponential time? All right. All right. So you can take courses. I bet you well, Jackie's taken this from me. So if you went and asked Jackie, he would know that I set you up on this. All right. But, you know, plenty of people would say this is an order n algorithm, right? And it is. It's an order capital N algorithm. And if you wrote that down, order capital N algorithm, that wouldn't be so bad, right? Because it is. The running time is order capital N, right? But the size, the amount of work it takes me to give you the input, I give it to you in bits or in decimals, right? So my work is little n, which is the log of that, right? And your work is exponential in my work, right? Remember, we already did this example. I give you a value n, capital N, and you count to it. Do you guys really want to play that game with me? No. Why don't you want to play the game with me? Because you know I'm right. Right? Does that make sense? All right. Let's not get into these scary things. And students get really hard with this. So let's not spend too much time with this either. All right? I'm not going to put it on the test, and if it comes up, we'll talk about it. All right? So if I'm multiplying two numbers together, then the number of bits is kind of log of the values, right? The size is the log of the values. But if I'm talking about the input being in values, then I might say that the size of the input is in objects, right? We don't want to get in here. We don't want to get into the hassle of log bits per, right? Let's just call the size. If I give you in objects, call the size of the input in. And if I give you two objects, let's not call the size of the input 2, right? Let's call it how many bits does it take for me to give you those two objects? Right? Does that make sense? And that just helps us deal with things. All right? Everybody good? And otherwise, let's not worry